we begin studying inferential statistics. So remember, inferential statistics was inferring something about the population as a whole from sample statistics. We only consider two parameters this semester: the mean and the proportion. And we will only ever look at single variable. Right, as you move on, you'll probably look at chi-squared, F distributions, so doing stuff with the population variance and standard deviation, doing a multi-mean test, multi-proportion test, things along those lines. We start with confidence intervals. Point estimate of a parameter is just a value of a statistic that is used to estimate the value of an unknown parameter. So we use a point estimate to make a claim about a parameter. A confidence interval is an interval of values used to estimate the value of an unknown parameter. It's constructed using that point estimate along with a percentage that we call the confidence level, somewhere between 0 and 100%. This specifies how confident we are that the parameter lies within that interval. This confidence level represents the expected proportion of intervals that will contain that parameter if a large number of samples is obtained. A very common confidence level used is 95%. Notice what it's not saying. It's not saying there's a 95% probability of the parameter being in the interval. It's a 95% confidence that it's in the interval. Remember, as with any estimation, there is error. So sampling error will occur. Since it is extremely unlikely, the sample mean is actually the true population mean. The margin of error is the maximum error when estimating the population parameter of interest using confidence intervals. The margin of error we take as half the length of the total interval. So we'll calculate the margin of error. And it'll go that error to the left and that error to the right. The center is going to be the point estimate. If you fix your confidence level, you can increase precision by increasing your sample size. If you hold sample size constant, you can increase precision by increasing confidence level. When trying to guess population mean, you have two scenarios. The first scenario is you happen to know the population standard deviation. The second scenario is you do not know the population standard deviation. That first case is extremely unlikely. If you already know the population standard deviation, it's very likely you already know the mean. Just to calculate standard deviation, you need mean. Which means in real life, that scenario is very unlikely. But it is a good place to start. That's the scenario we look at today. When sigma is known. First, it's going to have to be a simple random sample taken. And in fact, that's always going to be the case. Second, your population will have to be normal, or your sample size is at least 30. So the central limit theorem has to be satisfied. Because what we're doing is we're making a guess on the distribution of means. For this scenario, your standard deviation of population must be known. So we will need some critical values. Or we will need a critical value. The critical value is a z-score, and it's dependent on your confidence level. So these are some very commonly used confidence levels. 90%, you're going to use a z-score of 1.645. 95% is 1.96. That one is the most commonly used. So you'll probably have 1.96 memorized. 98%, 2.326, 99%, 2.576. If your confidence level is anything but one of those four. You have to find the z-score on your own. This is done by first finding an alpha value. This alpha is 1 minus your confidence level. It happens to be known as a significance level, and that will be important later. Divide that by 2. Then find the z-score that has that area, alpha over 2, to the right. Remember, it's symmetric, right? So what you could do is you could just find the z-score that has that area to the left and take its absolute value. So what you'll notice is at 95% confidence, 1 minus that is 5%, right? Half of that is 2.5%. So you look in your z's table. Z-score that has 0.025 area to the left is negative 1.96. Then the confidence interval can be found as your point estimate for the mean, x bar, plus or minus that critical value times sigma over square root of n. Note that that latter half is your margin of error. All right, so typically we would find the margin of error first and then construct the confidence interval as x bar minus e to x bar plus e. But now let's say you want to construct this confidence interval with a specific margin of error in mind. When you have to decide what sample size to use. Well, that's an easy formula. You essentially just solve for n. Right, you'll get the critical value times sigma all over e all squared. But remember, sample sizes have to be whole numbers, right? So you're going to have an option of either rounding up or down. You always want to round it up. Rounding it down is not going to guarantee your margin of error. It's actually probably going to give you a larger margin of error than you want. Whereas rounding it up will give you a smaller margin of error than you are looking for, which is better. No, but then I introduce a function that always rounds up. Remember the ceiling function? So I will typically be writing I typically write that, and then I can ignore that bit. Because that's what the ceiling function does. But for posterity, I will just leave it as normal. So as we've been doing before, 3 sets of problems. We'll do some by hand, some on the calculator, and some using Excel. Random sample, 60 customers at a clinic has a mean waiting time of 18.4 minutes. Assumed population standard deviation is 5.2 minutes, and the population is approximately normal. That actually doesn't matter because we already have a large enough sample size. We want a 95% confidence interval for the true mean wait time. I don't know what kind of clinic that is. So if you ever gone to a quick clinic for health, if you're waiting 18 minutes, that's really, really short. Even with an appointment, you're still waiting for an hour. First, we need margin of error. So remember, margin of error critical value times standard deviation divided by root A. For the critical value, oh, this is nice. It's 95% confidence. Which means it's 1.96. I don't have to look for it. So maybe I should here, right? And with that entire section, you might want to write those down on your reference sheet, just so you don't have to keep looking. Why not? Let me calculate margin of error, confidence interval, and this one has important formulas. Times So they told us what the population standard deviation is. It's 5.2 divided by the square root of our sample size. Here, 1.316. So again, make sure you can get that. Our 95% confidence interval. Sample mean minus that margin of error to sample mean plus that margin of error. So 18.4 minus 1.316 to 18.4 plus. $17.084 to 19.716. That's it for finding sample size. Just so I shrunk that up to 3 decimal places. Sample size always goes up to the nearest whole number. Now for the interpretation. So we are 95% confidence, or we can say with 95% confidence, along those lines, that the true mean wait time at this clinic is between 17.084 .804 minutes, and 19.716 minutes. Again, it is not a 95% probability that your true mean wait time is within there. It is 95% confidence. Or 95% of your intervals of sample size 60 will contain the true mean. And so what you could say no, that wouldn't work either. Yes, it would. If you randomly select a confidence interval created using the sample size 60, 95% chance it's going to contain the mean. What we could do is now you have that. I could now ask you, a manager claims that the mean wait time is 15 minutes. Could you say his claim is supported? That was 15 in that interval. It's not in there, is it? So his claim's unsupported. Call center takes a random sample of 45 calls, finds the mean length of the call is 6.3 minutes. Historical data say that the call length, standard deviation, is 1.8 minutes. And that the call lengths are approximately normal. Find 98% confidence interval for the true mean call length. Well, now we're using a 98% confidence. Is that our margin of error? Our critical value, though, is now 2.326. Times the population standard deviation of 1.8 over square root of our sample size. I got 0.624. So the confidence interval, always x bar minus e to x bar plus e. What is that going to give us? Yeah, 5.676 to 6.924. And this one's not asking for interpretation, so you get one. "38 students reports daily mean screen time of 4.7 hours. Soon prior data suggests that the standard deviation is 1.5 hours, and daily screen time is approximately normal. We are asked to construct a 90% confidence interval for the true mean screen time. So what you're going to do is you're going to have to find your stat menu. Menu, and so you want your stat menu and you want confidence intervals. We want a Z interval, right? Or a one sample Z interval. Depending on the calculator you have, it may ask you for your input method. Stats. I wouldn't worry about that ever on the calculator. You already have data, you probably just be using some kind of statistical software on your computer to do it. All right, so then you're gonna have to input several things. First, since this is Z, we need the population standard deviation, which was given to us 1.5 hours. You need your sample mean. That was 4.7 hours. You need your sample size. That was what, 38? And the confidence level as a decimal. They wanted 90%, right? So 0.90. So again, depending on the calculator you have, things can change the output. But I'm getting what the mean was, so I can always just check to make sure everything's in there, right? This was the margin of error. Sample size, population standard deviation, and then the lower limit and the upper limit. I'll just paste that right in there. Right, so again, unless you're asked to do it by hand, you just use your calculator. Look how quick that was. So now we're being told, suppose exam scores are approximately normal with a population standard deviation of 10, and historically the mean is 79. You take a simple random sample of size 16 and plan to look at the distribution of the means. We want the cutoff value so that 90% of all sample means fall at or below C. Why is that in here? I have no idea why that's in here. Whatever, should be good. So remember, this is going to be an inverse norm. They're asking for the 90th percentile, right? So that 90% fall at or below. Mean was 79. Typo from my notes, probably whatever. And the deviation so 91.82. Random sample of 50 items from a production line has sample mean weight of 61.2 grams. Assume population standard deviation is 2.4 grams. And using a normal model is appropriate. Construct a 95% confidence interval for the true mean weight. Apparently, so equals confidence dot norm. First, you need your alpha. What was the confidence level? 95%. What is alpha? That's Z. What is alpha? It was on that same slide. Look at the title of the Z-scores. Tells you what alpha equals. Yeah. Alpha, the significance level is 1 minus the confidence level. So it's 1 minus 0.95. .05 is our alpha for this problem. Then we need the population standard deviation. It's 2.4. Then we need the sample size, which was 50. So what this should do is give the margin of error. Just move this over. Call that our margin of error. Then what I'll do is I'll create a CI lower and a CI upper. Now remember the lower is going to be your mean, which they told us was 61.2, minus margin of error. Which we already have stored as B1 for this column. Otherwise, you just type in that formula. There's the lower limit. Well, the upper is going to be the same thing, isn't it? Except it's going to be plus. What I'll do again is just kind of paste those on the slides. So sadly, Excel doesn't have a feature to just do the interval right off the bat like the calculator does. So we want learn how to spell. we want to estimate the true mean delivery time for an online grocery service. We believe population standard deviation is 12 minutes, and we want a 20 or 95% confidence interval with a margin of error at most 3 minutes. How large of a sample should be used? So we want our E to be less than or equal to 3. So what we do is we just take E to be 3. Remember, sample size. Is the ceiling of Z, alpha over 2 times sigma all over E all squared. %95 confidence means Z is what? They told us sigma. Divided by 3. Square it. And then we round it up. Now, a few ways we can do this. So you could just do that and then round that up. 62. If you have this calculator, it has the ceiling function built in. So all I have to do is use the ceiling function. And it gives me 62. Excel should also have it built in. Let's check that now, actually. Does. Don't know why they changed it from ceiling to ceiling.math, but what do I know? Right, then we just put in our formula. I think that's all I need. Let's find out. Right, so regardless of how you do it, we get 67. Now keep in mind that this sample size, the 62, is a minimum. So you want to use no less than 62. Obviously, the larger your sample size, the lower the margin of error is from 3. Right, then what you do is you actually go out and do your sample size of 62 survey, get your mean, and then find the confidence interval from there. Questions on confidence intervals? So obviously the easiest way is just your calculator. And so again, you should probably be working with your calculator at home, trying to find where that stat menu is. So you can find all these quickly and use them for the test and exam. Speaking of tests, I believe there were tests due on Thursday. Yeah. Oh, and the second project is due. There is another announcement. We don't have classes next week. So for those who this is your second year here, they changed. It used to be Thanksgiving, Tuesday followed Thursday schedule, and Wednesday followed Friday schedule. This year they decided just to close on Tuesday through Friday. Not tell anyone, so none of us knew. So I know a lot of instructors were like planning on Tuesday and Wednesday classes. So the only day that the college is open next week is Monday. So that's exciting.